Hello everyone, in this video we are going to talk about exponents and powers. We come across many measurements in our daily life. For example, if we want to find the length of a pencil, we can easily measure it in few centimeters. If you want to measure the length and breadth of a book, even that can be measured easily in centimeters. So most of the measurements we deal every day are either in centimeters or meters or in kilometers if we talk about distance between two places. So what about measurements that involve huge distances or maybe very small measurements? For example, the distance between Sun and the Earth. It's a very large number 1496,000,000,000,000. So it becomes difficult to read such huge numbers. The mass of the Earth is again a very large number which is very difficult to read. Size of a red blood cell is 0.000075 meters, which is a very small number. So how do we deal with very large and very small numbers? Ideally, these numbers are difficult to read and understand, or they are even difficult to compare. So what do? We use exponents that make these numbers easy to read, understand, or even to compare. Exponential form, it is a way of writing large numbers in short form. For example, when we say we have to add 2 7 times, we say 2 plus 2 plus 2 plus 2 plus 2 plus 2 and plus 2. So we calculate it as 2 cross 7, which is 14. Now, in case of addition, if we have to multiply 2 7 times, it becomes 2 to the power 7, where 7 is called the exponent and 2 is called the base. If we think of a variable a and we add it 5 times, the answer would be 5a. But if we multiply the variable a 5 times, we get the answer as a to the power 5. So in case of addition, the coefficient of the variable is increased, and in case of multiplication, the power of the variable increases. B into B into B becomes B cube. We can even have a combination of numbers or variables. For example, A multiplied by B into B into B. So this becomes A square B cube. So we can add powers only for the same variable. The power of A is added the number of times A is being multiplied, and the power of B is equal to number of times B is being multiplied. Let's look at few examples that involve powers of positive numbers. The first example is 3 to the power 5. It can be written as 3 cross 3 cross 3 cross 3 cross 3 in the product form, which evaluates to 243. 5 to the power 3 can be written as 5 cross 5 cross 5, which comes out to be 125. If we have a combination of both these, 5 cube multiplied by 3 to the power 5, it becomes 5 into 5 into 5 into 3 into 3 into 3 into 3 and into 3, which evaluates to 30375. 3 square multiplied by 10 square becomes 3 into 3 into 10 into 10 in the product form, and the value is 900. 5 into 10 to the power 3 becomes 5 into 10 into 10 into 10, which comes out to be 5000. If we have fractions 2 upon 3 whole cube, then this becomes 2 by 3 multiplied by 2 by 3 multiplied by 2 by 3. So the power means that the number itself is multiplied the number of times equal to the power of the number. So in this case, the answer will be 8 upon 27. We multiply all the numerators together to get 8, and we multiply the denominators together to get 27. The next example is a combination of two fractions, 2 by 3 whole cube multiplied by 1 by 4 whole square. So this becomes 2 by 3 multiplied by 2 by 3 multiplied by 2 by 3 multiplied by 1 by 4 and then into 1 by 4 in the product form. When we find the value, we multiply all the numerators together to get 8 and all the denominators are multiplied together to get 432. So the answer is 8 upon 432. The next example is 2 by 3 cube into 10 cube. So this becomes 2 by 3 into 2 by 3 into 2 by 3 into 10 into 10 into 10, which comes out to be 8,000 on multiplying all the numerators together, and the denominators together give 27. So this is 8,000 upon 27. So we have seen if we are given any number in exponent form, how do we write the product form of the number and how do we find the final value. Thus, for any non-zero positive rational number a to the power n, it is equal to a multiplied by itself n times. And if it is a fraction a upon b whole to the power n, then the fraction a upon b is multiplied by itself n times. Now let's look at some powers of negative numbers. The first example is minus 3 to the power 5, which is written as minus 3 multiplied by itself 5 times in the product form and evaluates to minus 243. Here 3 has been multiplied by itself 5 times to get 243, and minus 1 is multiplied by minus 1 5 times to get the minus sign in the answer. The next example is minus 5 cube. This is equal to minus 5 multiplied by itself 3 times in the product form, and then the final value is minus 125. Here again 5 has been multiplied 3 times to get 125, and minus 1 is multiplied 3 times to get minus sign in the answer. Minus 3 to the power 4. This is written as minus 3 multiplied by itself 4 times in the product form and evaluates to plus 81. Here 3 is multiplied by itself 4 times to get 81, and the minus sign is multiplied by minus sign 4 times to get positive sign. So if we have even power for a negative number, then the answer is positive. But if we have odd power for a negative number, then the answer is negative. Minus 5 square, again the power is even. So this becomes minus 5 into minus 5, which evaluates to plus 25. Let's look at some fractions now. This is similar to the powers of positive fractions we have seen earlier. Minus 2 by 3 whole to the power 3. This is written as minus 2 by 3 multiplied by itself 3 times in the product form and evaluates to minus 8 upon 27. Here all the numerators are multiplied together to get minus 8, and all the numerators are multiplied separately to get 27 as the denominator for the answer. The next one is minus 3 upon 5 whole to the power 4. Again in the product form it is written as minus 3 upon 5 multiplied by itself 4 times. On multiplying the numerators we get plus 81, and on multiplying the denominators we get 625. The last one is a combination of two negative numbers with different powers. Minus 5 cube multiplied by minus 3 to the power 5. This is written as minus 5 multiplied 3 times and then minus 3 multiplied 5 times in the product form. The final answer is positive, because in this case the sum of the powers of both the negative numbers is even. 5 plus 3 is 8. So the overall power of the product is even. Hence the answer is plus 30375. Thus for every non-zero negative rational number we have minus a to the power n equal to minus a multiplied by itself n times. Minus a upon b to the power n is equal to minus a upon b multiplied by itself n times. So when minus 1 has an odd power, the answer is negative, and when minus 1 has an even power, the answer is positive. Now let's see how we can convert certain numbers to exponent form. For example, 243. We first find all the prime factors of 243. In this case, it is 3 cross 3, cross 3, cross 3, cross 3. So this is written as 3 to the power 5 because 3 is being multiplied by itself 5 times. The next number is minus 125. We keep the negative sign aside and then find the prime factors of the number, that is 125. The prime factors are 5 cross 5 cross 5. So in the exponent form, we write it as minus 1 to the power 1 multiplied by 5 cube. The next one is 30375. Again, it is a composite number, so we find all the prime factors of this number, which comes out to be 3 cross 3 cross 3 cross 3 cross 3 multiplied by 5 into 5 into 5. Here 3 is occurring 5 times and 5 is occurring 3 times. So the exponent form of the number would be 3 to the power 5 multiplied by 5 cube. The next one is 900. The prime factors of 900 are 2 into 2 into 3 into 3 into 5 into 5. So this can be written as 2 square multiplied by 3 square multiplied by 5 square. Next one is minus 5000. The prime factors are minus 1 into 2 multiplied 3 times and then 5 multiplied 4 times. So the exponent form becomes minus 1 to the power 1 multiplied by 2 cube multiplied by 5 to the power 4. Next one is a fraction. So we separately find the prime factors of the numerator and the denominator. The prime factors of 8 are 2 into 2 into 2. And for 27 it is 3 into 3 into 3. So this becomes 2 cube upon 3 cube. Next one is 8 upon 432. The prime factors of 8 are 2 into 2 into 2 and the prime factors of 432 are 2 into 2 into 2 into 2 multiplied by 3 into 3 into 3. Here we cancel out the common factors between the numerators and the denominators. So the 3 2's get cancelled out and we are left out with 1 upon 2 into 3 times. So it is 1 upon 2 into 3 cube. The last one is 8000 divided by 27. So we write the prime factors of 8000 in the numerator and the prime factors of 27 in the denominator and then convert it to exponent form. 2 is repeated 6 times in the numerator and 5 is repeated 3 times, whereas in the denominator we have 3 multiplied by itself 3 times. Now let's see how we multiply two numbers with the same base and different powers. For example, 2 cube multiplied by 2 to the power 4. 2 cube is equal to 2 multiplied by itself 3 times and 2 to the power 4 is equal to 2 multiplied by itself 4 times. This means 2 cube into 2 to the power 4 becomes 2 multiplied by itself 7 times, which means 2 to the power 7. So what do we see? 2 to the power 3 multiplied by 2 to the power 4 becomes 2 to the power 3 plus 4. So when we have same base and different exponents and the two numbers are being multiplied together, we get the same base and sum of the exponents as the power of the result. That is 2 to the power 7 in this case. This is called the first law of exponents. Any number a to the power m multiplied by a to the power n gives a to the power m plus n. So the product of same base with different powers gives us the answer with powers added. Now what do we do in case of division? For example, 2 to the power 4 divided by 2 cube. Again, two numbers with the same base but different powers are being divided. 2 to the power 4 is 2 multiplied by itself 4 times and 2 cube is 2 multiplied by itself 3 times. So 2 to the power 4 divided by 2 cube becomes 2 multiplied by 4 times divided by 2 multiplied by 3 times. Here the common factors get cancelled out and we are left out with just 1 2. If we observe, the powers of the two exponent numbers have been subtracted to get the power of the result, that is 4 minus 3 becomes 1. So the answer is 2 to the power 1, which is 2. This is called the second law of exponents. Any number a to the power m divided by a to the power n gives a to the power m minus n as the answer. Thus, the quotient of same base with different powers involves subtraction of the powers of the exponents to get the power of the result. Now power of a power. If we have 2 cube whole to the power 2, how do we evaluate this? First we expand 2 cube and see what it means. It is 2 multiplied by itself 3 times, and the square of this number would mean 2 multiplied by itself 6 times. So the answer becomes 2 to the power 6. Again, if we observe, the powers have been multiplied together to get the result. 2 cube whole square becomes 2 to the power 3 multiplied by 2, which is 2 to the power 6. This is the third law of exponent, which says any number a to the power m and whole to the power n gives a to the power m into n as the answer. Thus, power of power involves multiplication of the two powers to get the exponent of the result. The next is when we have two different numbers, that is two different base, and their exponents are same. On expanding both the numbers, we get 2 cube equal to 2 multiplied by itself 3 times, and 3 cube is equal to 3 multiplied by itself 3 times. Thus the overall answer is 2 multiplied by itself 3 times multiplied by 3 multiplied by itself 3 times. If we start pairing them up 2 and 3, we get 3 pairs with 2 multiplied by 3. So this becomes 6 multiplied by another 6 multiplied by another 6. That is 6 cube. So what do we see here? The two bases have actually been multiplied together and the power remains the same. So the overall answer becomes 6 cube in this case. This is called the fourth law of exponents. Any number a to the power n multiplied by any number b to the power n becomes the product of a and b whole to the power n. Product of different base with same power result in base getting multiplied and the power remaining same. What about division? We have two numbers with different base but same exponents. 4 cube divided by 3 cube becomes 4 cube upon 3 cube. On expanding 4 cube and 3 cube, we get 4 multiplied by itself 3 times and 3 multiplied by itself 3 times. Thus the overall answer on pairing up 4 and 3 becomes 4 upon 3 multiplied by itself 3 times. So in this case, if we observe, we are just dividing the numerator by the denominator and the exponent again remains the same. Any number a to the power n divided by b to the power n gives a upon b whole to the power n. This is called the fifth law of exponents. The reverse of this, if we see a upon b whole to the power n is same as a to the power n upon b to the power n. We can use the fifth law in either of these forms further for simplification. So the quotient of different base with same power involves the base getting divided and the power remaining same. There is another term called zero exponent. Let's take an example and see what it means. 4 cube divided by 4 cube is equal to 4 into 4 into 4 divided by 4 into 4 into 4. On cancelling out all the 4's, we get the answer as 1. Using the laws of exponents, if we see 4 cube divided by 4 cube will be equal to 4 to the power 3 minus 3, which becomes 4 to the power 0. So what does this mean? 4 to the power 0 is same as 1. This is called zero exponent. Any number to the power 0 is equal to 1. A to the power 0 is 1. If we use some value, 2 to the power 0 is 1. 2000 to the power 0 is 1. 200 to the power 0 is 1. So any number we pick to the power 0 is always 1, whether it is a fraction or a negative number or a positive number. The answer is 1. Now what do we mean by a reciprocal? Reciprocal of 5 is 1 upon 5. Reciprocal of 5 square will be 1 upon 5 square. What is the reciprocal of 2 upon 5? It's 5 by 2. So the reciprocal of 2 by 5 whole cube will be 5 by 2 whole cube. In general, for any non-zero rational number p upon q, where p and q are not equal to 0, the reciprocal of p upon q to the power n is equal to q upon p to the power n. Let's now come to negative powers of a number. 2 to the power minus 3. Here the power is negative integer. This is called negative integral exponent. We know that 2 cube is equal to 2 multiplied by itself 3 times. So what does 2 to the power minus 3 mean? This is equal to 1 upon 2 multiplied by itself 3 times, which is 1 upon 2 cube. Similarly, 3 to the power minus 2 is equal to 1 upon 3 square. Thus, for any non-zero rational number a and a positive integer n, a to the power minus n is equal to 1 upon a to the power n. Thus, we say a to the power minus n is the reciprocal of a to the power n. Likewise, a to the power minus 1 is the reciprocal of a. Let's look at some fractions now. 3 upon 4 to the power minus 3 will be equal to 4 upon 3 to the power 3. In general, for any rational number p upon q whole to the power minus n, it is equal to q upon p whole to the power n. That is, the reciprocal of the fraction is taken here. So negative power means reciprocal with positive power. We take the reciprocal of the fraction and change the negative power to positive power. This is called negative integral exponent. How we convert a negative power to a positive power. Now where do we use these laws of exponents? The first use is in simplification of expressions. For example, we have 12 cube multiplied by 5 cube divided by 2 cube into 3 square into 15. Here we see there are two composite numbers. So the first step is to express all the composite numbers in powers of the prime numbers. 12 is equal to 2 square multiplied by 3 and 15 is 3 into 5. So the expression becomes 2 square into 3 whole cube and then 5 cube in the numerator. The denominator has 2 cube multiplied by 3 square multiplied by 3 and then multiplied by 5. On opening the brackets, it becomes 2 to the power 6 into 3 cube into 5 cube upon 2 cube into 3 square into 3 into 5. Here we have used the laws of exponents. For reference, all the laws of exponents are written above on the upper right corner. The third law of exponent has been used here to open out these brackets for 2 square into 3. The next step is to add up all the powers, collect the powers of the same base. 2 to the power 6 is in the numerator and 2 cube is in the denominator. So we say it is 2 to the power 6 minus 3. 3 cube is in the numerator and we have 3 square into 3 in the denominator. So this becomes 3 to the power 3 minus 2 minus 1. And then 5 to the power 3 minus 1. So the answer becomes 2 cube into 3 to the power 0 into 5 square. And we know that any number a to the power 0 is anyways 1. Thus the final answer is 2 cube into 5 square. The result of simplification should always have positive powers of prime numbers. There should not be any composite numbers involved and there should not be any negative powers. Let's look at another example involving simplification. 3 to the power minus 1 minus 4 to the power minus 1, both the numbers to the power again minus 1, plus 2 to the power minus 1 minus 4 to the power minus 1, again both the numbers having a power of minus 1. This equation involves all negative exponents. So first we change them to positives. 1 upon 3 minus 1 upon 4 whole to the power minus 1, 1 upon 2 minus 1 upon 4 whole to the power minus 1. We have changed the negative exponents only from within the brackets because we are going to solve the brackets inside out. On subtracting 1 by 4 from 1 by 3, we get 1 by 12. Likewise, on subtracting 1 by 4 from 1 by 2, we get 1 by 2. Now we again have two numbers with negative exponents. So we take the reciprocal of both of them and the exponent becomes positive. So the numbers become 12 plus 2, giving us an answer of 14. The next use of laws of exponents is in evaluating expressions. Let's take an example for this. In this example, we see many numbers raised to the power 0. And we know that a to the power 0 is 1. So any number with the power of 0 is equal to 1. So we put 1 in place of all these numbers. 3 to the power 0 is 1, 4 to the power 0 is 1, 2 to the power 0 is again 1. 1 minus 1 becomes 0. 1 plus 1 is 2. 2 into 1. So the final answer is 2. Let's take another example. 3 square whole cube multiplied by 2 to the power 0 divided by 3 to the power 0 into 3 square. First, we open out the brackets for 3 square using the third law of exponents. So the power of 3 becomes 3 into 2, that is 6. Now we replace any number to the power 0 with 1. So the expression becomes 3 to the power 6 multiplied by 1 divided by 1 into 3 square. We just have 3 left out now with different powers in the numerator and denominator. Finally, it becomes 3 to the power 6 minus 2, that is 3 to the power 4, which comes out to be 81. So laws of exponents are normally used to find the value of any of the given expressions. The next use of laws of exponents is to find the value of unknown exponent in an equation. For example, 2 to the power m plus 2 multiplied by 2 to the power minus 3 is equal to 1024. Here we have an equation that has 2 as the base on the left hand side and there is a composite number on the right hand side. For any equation, we first find the prime factors of the composite numbers involved there. In this example, 1024 can be written as 2 to the power 10. On equating left side to right side, the equation becomes 2 to the power m plus 2 multiplied by 2 to the power minus 3 is equal to 2 to the power 10. On using the laws of exponents, left side again becomes 2 to the power m plus 2 minus 3. The two powers are being added because we have two numbers with the same base being multiplied together but different powers. So we get a linear equation that involves only the exponent part of both the sides, that is m plus 2 minus 3 becomes equal to 10 because the base is same on both sides of the equation. So on solving this linear equation, we get the value of m as 11. So we can find the value of any missing exponent using the laws of exponents. Now we come to the standard form for very large and very small numbers. Let's take an example of large number first. In this example, if we keep on moving 10, factor of 10, then we get 5 multiplied by 1 followed by 9 zeros, which can be written as 5 into 10 to the power 9. So for any large number, the standard form can be written as k into 10 to the power n, where k is any number that lies between 1 and 10 and the power of 10 is a positive integer. Let's take an example of a small number. For example, this is the number. After the decimal point, we see there are 7 zeros. So this can be written as a multiple of 1 upon powers of 10. So finally this becomes 5 into 10 to the power minus 8. If we see here, there were 7 zeros and we need to bring the decimal point after the first digit we see here. So it becomes 5 into 10 to the power minus 8. This is the standard form for very small numbers. So small numbers can be written in the form k into 10 to the power n, where k lies between 1 and 10 and n is a negative integer. That is, the power of 10 in case of small numbers is negative. We have seen a few examples on the first slide where we encountered very large and very small numbers. Let's see how we can write them in exponent form. The distance between sun and earth is given here. Now in this case we need to move the decimal point back till we have only one digit left out on the left side of the number. So the exponent form is equal to 1.496 into 10 to the power 12. Here we have taken 12 jumps to reach this point between 1 and 4. So that's why the power of 10 is 12. The size of red blood cell is 0.0000075 meters. Again in this case we move the decimal point to the right till it crosses one digit. So the number of jumps involved becomes a power of 10, but it has to be negative in case of small numbers. So it becomes 7.5 multiplied by 10 to the power minus 6. So in case of small numbers, we move the decimal point to the right till ahead of one digit, and the power of 10 is negative. The power of 10 is positive for large numbers and it is negative for small numbers. So the standard form of exponents in general is k into 10 to the power n, where k lies between 1 and 10 and the power of 10 is an integer. For large numbers it is positive and for small numbers it is negative. Now how do we convert back from exponent form to the usual form of a number? The distance between sun and the earth is 1.496 into 10 to the power 12. In this case, we move the decimal point 12 steps forward and we get the large number that denotes the distance between sun and the earth. For small numbers, again the size of red blood cell is already given as 7.5 into 10 to the power minus 6. So in this case, we move the decimal point backwards by 6 steps because the power of 10 is minus 6. Thus the size of red blood cells becomes 0.0000075. So the decimal point is moved to the left equal to the absolute value of the power of 10. Now how do we compare any two large numbers or maybe small numbers? For example, 41.3 into 10 to the power 14 and 4132 into 10 to the power 13. Which one is greater? First, we convert both the numbers to their standard form. 41.3 into 10 to the 14 becomes 4.13 into 10 to the power 15 and 4132 into 10 to the power 13 becomes 4.132 into 10 to the power 16. Now we compare the power of 10 and we see that the second number is greater. So finally we write the answer in terms of the original numbers given in the question, and the answer is 4132 into 10 to the power 13 is greater than 41.3 into 10 to the power 14. For interesting articles, you can visit the website www.mathkeyacademy.com. For any queries, you can send an email to mathkey.academy@gmail.com. And for more such videos, subscribe to the YouTube channel Mathkey Academy. And if you like the video, don't forget to click the like button.